So the last thing we did was talk about converting, and I want to at least revisit this one here because we did it kind of fast. So when we're converting between polar and rectangular, we use these four equations that are over here to the side. And when we are going to Cartesian or rectangular, that's the easiest. If you're given polar, that means you know r and you know theta. And so you just have to plug them into these two equations, and bingo, you've got x and you've got y. So that's why those are so easy. So here, this first one is going to be -4 cosine of 3 pi over 4. And if we look at 3 pi over 4, cosine is -√2 over 2. So -√2 over 2 times -4 gives us the 2√2. And similarly for the second one, we're just doing y equals r sine of theta. So r is -4. Sine of theta is +√2 over 2. So we have -4 times +√2 over 2, which gives us that. Now you can also, if you're comfortable thinking in vectors, another thing you can do, if you looked at the unit circle point right here, this unit circle point is -√2 over 2, comma √2 over 2. And then this radial distance is 4. We're trying to get out here to, let's see, I'm going in the opposite direction now. I'm going to go down this way because we have a -r value. So we're trying to get to that point right there. If you take the unit circle point and multiply it by a scalar, it's going to pull you to the right place. So like if we take that point right there and just multiply it by -4, it's going to give us that point down there. You know, that's essentially what these equations are doing mathematically, but geometrically you can think about taking the point on the unit circle. So at 3 pi over 4, the point on the unit circle is that, and then you just scale it by r. You just take that point and multiply by r, and you get that point. You know, traditionally we can't take an ordered pair and scale it, but if you think of it as a vector, you can scale it. All right, so let's take a look at these two. And sometimes it's easier to look at the unit circle. Like this one here has, let's see, I'm looking for, so here we are converting to polar. So this direction is a little more work. When we look up here, we don't have an r or a theta that's isolated. So we've got to kind of grab a couple equations and then solve for theta or solve for r. So it's not as immediate as going to Cartesian from polar. So we have to be a little more creative. Generally, we're looking at the last two equations there. And we're trying to get because this one, the only polar letter in this one is r, and the only polar letter in that one is theta. So usually it's those two that we use if we're given Cartesian and we want to get to polar. So let's go with r first. So r squared is the sum of the squares of the coordinates. So here we could say that r squared is going to equal 1 plus 3 if we square the x and we square the y. So r squared is going to be 4. So r will be plus or minus 2. And as we've seen, there's lots of different representations of a polar point. We could choose the positive r and then have a positive or negative theta. We could choose the negative r and then have a positive or negative theta. Generally, we will choose the standard representation, which is positive r, positive theta, and theta is between 0 and 2 pi. That's the standard representation. So there's our, so we'll choose the positive 2. And now to get to theta, we can do it super analytically and just grab that formula. Tangent of theta is y divided by x, tangent is slope. When we're looking at a line through the origin, tangent is slope. So tangent of theta in this case is going to be equal to y over x, that's √3. So now we go to our unit circle and we think about where is tangent √3. hopefully you can sort of visualize it by now. So when we're looking at the tangent values and we have a root 3, we're thinking about the 12-sector unit circle, the unit circle that's based on pi over 6, not the 8-sector circle that's based on pi over 4s. So this one is the clock, right? This one, when you break it into the 12-sector unit circle, you're dealing with a clock. 12 pieces of pi over 6, or 12 pieces of 30 degrees, 12 sectors. And tangent on the unit circle, when you're looking at lines through the origin, your terminal ray is a line through the origin. Tangent is slope. And this one right here has a slope of root 3. This one right here has a slope of root 3 over 3. If you were to look at your unit circle coordinates and form the slope, you'll get that. So this one down here also has a slope of root 3. And then similarly, this one's going to have a slope of root 3 over 3. And then these ones over here will be negative. So this one is going to be negative root 3 over 3. This one is going to be negative root 3. So at any rate, when we look for tangent being root 3, that means that we're on that terminal ray. And so you could choose this angle. You could choose this angle. You could choose this angle. You could do all sorts of things. But generally what we're going to do is pick the smallest positive angle. All right. So we're going to say that theta will be pi over 3. So we're going to choose the smallest positive angle. So pi over 3. Now, let me just point out one thing, because a lot of you may be inclined just to write this, which is not bad, but we've got to be a little bit careful. You may be inclined to write this. And that is true. Let me just point out the difference, though. This is a trigonometric equation that has an infinite number of solutions. Right? You can plug in pi over 3 as the solution. You could plug in down here and get to 1, 2, 3, whatever that number is. I can't even count right. 1, 2, 3, 4, 5, 6, 7, 8. So that's 4 pi over 3. So 4 pi over 3 is a solution. Minus 2 pi over 3 is, there's an infinite number of thetas that satisfy that. This only has one solution. Inverse trig functions. Did I hit record? I did. Inverse trig functions. So a function only has one answer, right? And so when we're looking at this function here, we restrict it and we say the inverse tangent is an angle on the right side. So this would have only one answer, and in this case it will be the right answer. The place where it won't be the right answer necessarily is if this was a negative here. If this said inverse tangent is negative root 3, so if we did that, we'd have theta equals inverse tangent of negative root 3. That answer, if we stay on the right, would be negative pi over 3, and that's not the smallest positive angle. So if we do that inverse thing, we've just got to be a little careful because we generally are going to, we want to choose the smallest positive angle. So if you have an inverse trig function of a negative number, that might be giving you a negative angle. In the case of inverse sine or inverse tangent, it would be giving you a negative. So we just have to be a little bit careful. So the standard representation here, we are going to choose 2 comma pi over 3. And I'll put a little p down there just to emphasize that it's impolar. But that would be our representation. Now, sometimes it's easier to just go visual. And let me point out something here. This point is not on the unit circle, but it's close to being on the unit circle, right? If we divided both coordinates by 2, it would be on the unit circle. And so you could get at it that way. So if we thought about this point, right there, we could say, okay, well, the unit circle value, let's suppose that the unit circle is right here. So this point would be 1/2 comma root 3 over 2. Yeah. So if we take that point and we multiply that point by 2, we get to this. So this point in polar is pretty obvious. It's r comma theta. It's 1 comma pi over 3. And then if we just scale it by 2, we would get to that point. Right? So we scale, right? To get to here, we're 2 units away. So we would take that point and multiply by 2. So you could take the polar point and scale it. Leave the same angle, but scale the radius. You could think of it that way. Now, and that brings up a point like this. This may be a lot easier to just visualize and get to the answer instantly. 0, -9, we are down here. Can you see what the r value is? How far is that point from the origin?
-9.
It's 9 from the origin, though. So when we think about distance to the origin is 9. Yes, if we go with one of the contrarian concepts of radius, you could say, oh yeah, -9. But the distance to the origin is 9. And when we think about our standard representation, we want to think about distance. And what is the angle there?
3 pi over 2.
Yeah, 3 pi over 2. So here you can just sort of look at the point and see what the polar representation should be. It's going to probably be a little bit easier than doing, you could do r squared equals x squared plus y squared. Of course you can do this. You get this, so x squared plus y squared is going to be that. So then r will be plus or minus 9. It's best to choose the positive. And then you could say tangent of theta is equal to y over x. That's undefined. So then you'd have to go to the unit circle and say, oh, where's tangent undefined? It's undefined at the bottom and at the top. And we're down here, so you would choose the 3 pi over 2 as the place where tangent is undefined. Okay, so that's sort of going back and forth between polar and Cartesian. In any coordinate system, one of the first things we generally investigate is the basic equations for that coordinate system. So when we think about Cartesian, and we talked about this on Tuesday, the 2 coordinates that we have are x and y. And if we're in R2, x equals a constant, it's a vertical line, y equals a constant, it's a horizontal line. So those are our 2 basic equations in R2. When we come to polar, we have 2 coordinates. We have an r and a theta. So we want to ask the same thing. Well, what is r equal a constant equal, and what is theta equal a constant equal? Or what is the graph of theta equal a constant? So the graph of r equal a constant, graph of theta equal a constant. In polar, graphing a circle is super easy. So if we say r is equal to a constant, and there's no theta in the equation, it means that theta can be anything. Just like in Cartesian when we graph a line, a vertical line. When we say graph x equals 3 in Cartesian, there's no y in the equation, which means there's no restriction on y. So we want all the points where x is 3 and y can be anything. Over here, if we say we want all the polar points where r is equal to this constant a, that means theta can be anything, because theta is not in the equation. The equation restricts the variable that's in the equation. So this says r must be equal to a. And so if r is equal to, say, 2, then this is a circle of radius 2. So if you go into Desmos and graph in polar and just graph r equals a constant, you're going to get a circle. Even if it's r equals a negative constant. In polar, that will still graph. It's just going to graph it in the opposite quadrants. So if this was r equals -2, when we're at pi over 4, we would actually graph that point. When we're at 3 pi over 4, we would actually graph that point if r was -2. Because that negative is going to bounce you 180 degrees into the opposite quadrant. So r equals any constant will be a circle centered at the origin. Now, one of the reasons we allow these negative r values is for this. When theta is equal to a constant, so say theta is equal to whatever this is, say, it's not quite pi over 4, just say pi over 4. So if theta is equal to pi over 4, that means we want all points where theta is pi over 4 and r can be anything. Well, if r is positive, we would only get a ray. But if we allow this weird polar twist and say, ooh, let's allow negative radial values, then you would also get the ray in the opposite direction. So theta equals a constant angle is going to give you the entire line through the origin based on whatever that constant angle is. So you'll get a whole line. And the other equation that we often look at is the identity equation. When we think about Cartesian and we think about the identity equation is where you set your two variables equal to each other, y equals x. That's what that looks like in Cartesian. We get that diagonal line. In polar, the identity equation is going to be that spiral. When we let r and theta be equal to each other, so as theta increases, we're rotating counterclockwise, the r is increasing, pulling us further from the origin. So that's the identity equation in polar. It's that Archimedean spiral. So that gives us a sense of how the graphing is going to begin in polar. Let's look at some polar equations. One of the funny things about these coordinates is that when you look at x and y, x is traditionally the independent variable, right? So we have x as the first coordinate is the independent variable. So traditionally, I mean, you can solve for x sometimes and turn it into the dependent variable. But traditionally, right, we're writing y equals a function of x. And so what's funny is that in polar, it's backwards. We do r comma theta, but whenever possible, we want to isolate the r. So we traditionally, in polar, are thinking about the theta as being independent. So we're thinking about plugging in a theta and getting out a radial value. And so it's funny that they do this flip thing. You would think that we would keep this same sort of convention that, ooh, let's have the second coordinate be the dependent variable, but no. I don't know why. Never figured that one out. But just be aware of that. So when we look down here at these polar functions, these polar curves, whenever we have a polar curve, if we can isolate r, we will. Okay. Now our equations that take us back and forth don't have cosecants, they don't have secants. So the first thing that we want to do is try to convert this over to the trig functions that we see in these four equations, our four standard equations that take us back and forth. And it's not too big of a stretch to realize that, hey, if we multiply both sides by sine of theta, we have now matched right there. And so we can take that r sine of theta and just replace it with a y. So here is our Cartesian equation. And what is that? What's the graph of that?
A horizontal line.
Horizontal line. So now we know what a horizontal line looks like with an equation in polar. That's what horizontal lines look like. If you have r equals 5 cosecant, you'd have the horizontal line of 5. If you have r equals 10 cosecant, you have the horizontal line of 10. So that's what horizontal lines look like in polar. So what we've seen so far today is that horizontal lines are easier to write the equation down in Cartesian, but circles are easier to write the equation down in polar because it's just r equals a constant. R equals the radius. Circle centered at the origin. So similarly over here, we're going to do the same thing. We don't have secants inside of our four gateway equations that are taking us back and forth. But if we multiply both sides here by cosine, we get that, oh, this is what vertical lines look like. Vertical lines are constant times secant. So that's what a vertical line looks like in polar. R equals -5 secant would be the vertical line at -5. So those equations can be used to convert a point in one of the coordinate systems to a point in the other, or they can be used to convert an equation in one of the coordinate systems to an equation in the other. So it can go both ways, points or equations. So let's take a look at circles. We just talked about circle centered at the origin. That's got the simplest equation, just r equals a, or negative a. A can be negative. You'll get a circle of radius a centered at the origin. If you want a shifted circle, then the equation looks a little different. That is going to be a circle of radius that, and it's going to be centered at a comma b. In this class, I'm not going to ask you to graph these on a test. We're going to look at a subset of these shifted circles, but not the most general shifted circle like that. So here are the two that we will encounter quite frequently. So if you look at this if this equation sort of has two pieces to it, if you just take one or the other piece, these are the circles we're going to look at. So if you take the sine piece, you're going to end up with a circle tangent to the x-axis. And if you take the cosine piece, you're going to get a circle that's tangent to the y-axis. If a is positive, you're going to be above or right. If a were negative, you would be left here or below here. So
it'll always be touching
yes,
the axis. Okay.
Right there at the origin. It's always going to be touching right at the origin, tangent at the origin, and we'll look at example in 1 sec. So the radius is always going to be half of whatever the coefficient number is. So the radius here is a, which is half this coefficient of 2a. And here's how we're going to graph them. So let's suppose we see a constant times sine or a constant times cosine. It's easiest if you already know where you're going. If you know that a constant times sine or a constant times cosine is a circle, then we can just plot a few points and we can graph it pretty easily. So constant times sine is a circle. Okay, well, let's plot a few points. Let's take our theta value. And when we think about theta, we're thinking about our counterclockwise rotation. I'm going to put theta on the left because that's what we're going to plug in to get to the r. So if we plug in theta equals 0, right there, sine of 0 is 0. The graph of r equals 0 is the origin. Over there. So 0 comma 0. And now let's just do our rotation. Rotating around, let's go up to pi over 2. Pi over 2. Sine of pi over 2. Sine of pi over 2 is 1. 1 times negative 4 is negative 4. So pi over 2, we come up to here. Pi over 2 is pointing north. But then our point is negative 4, so we have to bounce down there. And now if we get our rotation all the way over to pi, sine of pi is 0, so we're back to 0. So if we go pi, our radial value is 0, so we're back to this point. And if we were to then go to 3 pi over 2, we'd be back to this point. So if we know in our mind that r equals a constant times sine or cosine is a circle, if we know that, we're done. We now can infer that this is the only way we're going to get a circle, is if these 2 points were there. So our circle is going to be tangent to the x-axis. Ooh, that's horrible. I need to stand more in front of it, I think, to get it. So, wow, that's better. So there's our circle. So this is a combination. We're going to plot 2 points and use the fact that we sort of are hopefully cluing in that a constant times sine or a constant times cosine will be a circle. And it's always going to be tangent at the origin. So let's try this one. So same process. Let's plug in a theta. Let's get some r's. We plug in 0. So 0 degrees, 0 radians that way. Cosine of 0 is 1. 1 times 2 is 2. So in the 0 direction, that's to the right, our point is 2 units from the origin. So that's our first point. So theta equals 0 is over there. Now we rotate up. Pi over 2. Cosine of pi over 2 is 0. 2 times 0 is 0. So we're here. We're done. We know that there are 2 shadow points. One is right there, and one is right there. And our circle is going to be tangent at the origin again, but it's going to be to the right. So the cosine ones are always going to be a little shifted to the right. The sine ones are always going to be shifted vertically. This one is shifted down because of that negative. This one is shifted right because this is a positive. And I didn't write down this point here. So pi over 2, cosine of pi over 2 is 0. And if you started, if you go over to pi and then to 3 pi over 2, you just start repeating. So the period of these is pi. So if we looked at Desmos and graphed one of these, what we see is that all the points are plotted. Desmos is great for polar and parametric. So if we graph r equals 3 sine theta, it's going to be there. And if you put a negative, it's going to be below. And if you make this cosine, this is going to be to the left. If I can get in there and rewrite that as cosine. So you can play with a couple of these just to, it's to the left because it's negative. We make it positive, it goes to the right. And so if we graph only 0 to pi over 2, we're going to get half a circle. So Desmos is a good thing. You can play with these domains just to see. So these circles are graphed with a period of pi. Pi will get you all the way around. All right, let's go to some weirder stuff. So once again, we have polar equations. We have r's and thetas. We want to know what the rectangular curve will be. So once again, when we look over here, we see cosine, we see sine, and we see tangent. We don't see those functions over on that right side of the equation. So we need to do some work. So let's see. The first thing I'm going to do is write cotangent as 1 over tangent. And I'm going to write cosecant as 1 over sine. Now I see the 3 primary trig functions, a subset of those 3 primary trig functions. And we look at that sine, though, and we need an r with it. Right? We need an r. So let's multiply both sides by r. So if we multiply both sides by r, we now have matched. R sine theta is y. Tangent is y over x. And we've now found the equation in rectangular. We'd like to simplify it if we can. I didn't do my division very well, though, over here. What should this be? X over y or y over x?
X over y.
X over y, right? Because we're reciprocating tangent. So tangent is y over x, so if we reciprocate it, we get x over y. So let's isolate here. Let's rewrite this as x equals y squared. So there is our Cartesian equation. Cartesian equation, if we were asked to graph it, this is just the sideways parabola. That's going to look like that. Okay, now this one, hopefully you can kind of visualize it. You're looking at a circle of radius 3 centered at the origin, and you know that a circle equation centered at the origin is x squared plus y squared equals r squared. So you could write down x squared plus y squared equals 9. Now if we want to do it mathematically, though, what we are going to do is square both sides of this equation. So we're going to square both sides. So if you have 2 expressions that are equal to each other, their squares are also equal to each other. So you could do this. And then you look up there and you're like, oh, we have r squared on the right up there in the third equation. So that will take us to the equation x squared plus y squared equals 9. Okay. Any questions on that? Not too crazy. But it might get worse. So the most complicated graph that we are going to look at is the cardioid. The cardioid is going to be the most difficult of the graphs. But hopefully after we've talked about them for a few minutes, they're not going to seem that difficult. So cardioid, it's called cardioid because it looks kind of like a heart. Well, in that position, it looks like a heart. I don't know what it looks like in that position, but whatever you want to think of it as, you can. So if you want to call it a gluteoid instead of a cardioid, you could. The equation form of a cardioid will be R equals a constant plus or minus the same constant up to a minus. As long as these two magnitudes are the same, it's going to be a cardioid. So it doesn't matter. There could be two minuses, two pluses, a plus and a minus. Does not matter. As long as it's a constant plus a constant times sine or cosine, it's a cardioid. So if it is in this form, a plus or minus a cosine, a plus or minus a sine, it's a cardioid. So let's just back up for 1 second. So we've already seen that if we just have that, we have circles. But if we add this extra constant out in front, then we're going to have cardioids. And we're going to graph them in a similar way where we're going to look at kind of a wire frame or something, or whatever, however you want to think of it, a template. So when I look at these cardioids, I am seeing 4 important points on all of them. They all have these 4 important points, and they form a T. Like there's this capital T that's going to be formed for all these cardioids. There's going to be 3 points in a line and then 1 point further away. 3 points in a line, 1 point further away. So the idea is that if we can figure out those 4 points, those 4 key points, that kind of creates a frame, and then we just have to connect the dots. So let's just notice that with these cardioids, if we had these 4 points, from the 3 points that are going to be collinear, you sort of bubble out past those points. Like it's a kind of, very round shape. So when we look at this first one here, let's go through the 4 points. And we always do the same thing with polar. We start at 0, rotate to pi over 2, rotate to pi, rotate to 3 pi over 2. 4 points. So if we plug in 0 here, cosine of 0 is 1. 2 minus 2 is 0. So this point is plotted when theta is equal to 0. And then we rotate to pi over 2. Up to pi over 2. Cosine of pi over 2 is 0. 2 minus 0 is 2. So in the pi over 2 direction, we're going up to 2. So that is the point that's plotted when theta is pi over 2. And then we keep rotating. So we started at 0. We went to pi over 2. Now we're going to go to pi. Cosine of pi is negative 1. Negative 1 times negative 2 is plus 2. So now we have 4. So in the pi direction, we go 4 units out. That's what this point is right here. So that's theta equals pi. And then in the 3 pi over 2 direction, so rotate all the way around down to there, cosine of 3 pi over 2 is 0. 2 minus 0 is 2. So in the 3 pi over 2 direction, we go 2 units from the origin. So that's going to be theta equals 3 pi over 2. And then we just connect the dots. So we have to have it in our mind that a constant plus a constant times sine or cosine is a cardioid. We get our 4 key points and then connect the dots. Same thing over here.
Wait, I have a
Yeah,
question.
go. Yeah.
Why did that last one go negative and the pi over 2 was positive?
Okay, so when we plug in pi over 2, cosine of pi over 2 is 0. So 2 minus 0 is 2.
Yeah.
So in the pi over 2 direction, we go 2 because we got a positive radial value. When we plug 3 pi over 2 in, we also get 0. 2 minus 0 is still 2. but we have to go, if r is positive, we go in the direction of that angle.
Okay.
So 3 pi over 2 is our directed angle, and if we get a positive radial value, we're going to go in that direction. If we had a negative 2, we would bounce. But if we have a positive radial value, we go in the direction of the terminal ray. So let's try it over here. When theta is 0, cosine of 0 is 1, 2 plus 2 is 4. So when theta is 0, we're going to be 4 units in the 0 direction, in that direction. 4 units from the origin. When we rotate to pi over 2, cosine of pi over 2 is 0. So we get 2 plus 0, which is 2. So in the pi over 2 direction, we are going to go 2 units away from the origin. And then we rotate over to pi. Cosine pi is negative 1. So we're going to get 2 minus 2, which is 0. So in the pi direction, we go 0 from the origin, which leaves us at the origin. And then we rotate to 3 pi over 2. Cosine of 3 pi over 2 is cosine of 3 pi over 2 is 0. 2 plus 0 is 2. So we go 2 in the 3 pi over 2 direction. So those will be our 4 points, then we connect the dots. And similar for these. Same idea. I can't really remember. Let me just see what I put over here. Yeah, let's go. So you have these ones to look at that. I'm not going to go through the points right this second. Let's look at a one that's not graphed yet. Let's start from scratch. So you can look at those two to double check that you're understanding. So let's go here. So 0 direction. How far in the 0 direction should we go? I think I heard it. 8, yeah. So we're going to go 8 in the 0 direction. That is 8 units. It's positive 8, so we're going in the 0 direction. If it was negative 8, we'd bounce and be on the other side. Pi over 2. How many units in the pi over 2 direction are we going to go? 4. Because cosine of pi over 2 is 0. Pi direction, 0. 3 pi over 2 direction. So 3 pi over 2, this is going to be 0. So we're going to go down to negative 4, but we should be thinking that we're going 4 in the 3 pi over 2 direction. So we're going to go down to there. Now we're ready to connect the dots. It's easiest, I think, and it doesn't. You don't have to be. It just has to be a general, decent sketch, So that part is, probably the easier part for the 3 that are lined up, and then it just sort of bulges out a little. Don't make it super tight. It just bulges out, and so just make sure it's a little bulgy. All right, let's try this one. Okay, in the 0 direction. What's our radial value? 2. So in the 0 direction, that's to the right. We plug in our 0, we get positive 2, so we go in the 0 direction, positive 2. Pi over 2 direction? 0. In the pi direction? So we're going to end up at negative 2, so we're going positive 2 in the pi direction. So we're going to the left. And then 3 pi over 2? 4. So there it is. You can connect these two. Then it just sort of bulges out and kind of flattens out. It's almost like a horizontal tangent down there. Or, well, maybe I shouldn't say almost. It is a horizontal tangent down there. All right. So that's how we graph our cardioids. Constant plus constant times sine or cosine will be a cardioid. Let's see. Let's go back. I didn't have an example which I wanted to do, and I didn't. I don't know why. I should edit this a little. I want you to try this one. So let's suppose you have -3 minus, let me think for 1 second. Yeah, that'll be fine. So let's do this one. All right, so you all try to do that one on your paper and see if you can get her. Yeah. All right, so in the 0 direction, what are we getting?
-3.
So in the 0 direction, we plug in 0, this goes away, we get -3. So the 0 direction is to the right, but our radial value is negative, so we bounce to the left, and we're going to be 3 units away from the origin in the left direction. So that is theta equals 0. Theta equals pi over 2. Sine of pi over 2 is 1. So what are we going to be?
6 down.
6 down, because we'll get -3 minus 3, which is -6. So in the pi over 2 direction, we have a radial value of -6. So that means bounce the opposite direction, 6 units in the opposite direction. So that's theta equals pi over 2. And then when theta equals pi, so now we're in that direction, sine of pi is 0, but we have -3, so we go to the right 3 units, and we're going to be right there at pi. And then the last one, 3 pi over 2, so in the down direction, sine of 3 pi over 2 is -1. We end up with 0, so we're going to be right at the origin. So that will be theta equals 3 pi over 2. Then we just have to connect the dots, bulge out a little, get a horizontal tangent, and we get that cardioid, the heart. Not too bad. Kind of fun. Yeah. Very a little creative. Okay. Let's do calculus in polar now. Let's step it up. You ready? So, when we think about calculus and we go back to Calc 1, the 2 important concepts that we had, tangent lines and areas. So we want to do that same thing here. Now we have these polar curves. There's a lot of applications for polar curves where things are rotating. So you sort of see that there's a lot of symmetry with polar curves. And so we treat them differently than with Cartesian functions. But we want to use the same concepts. So the derivative, we talked on Tuesday about the derivative of a parametric curve. And the derivative of a polar curve is really similar. With a parametric curve, we did dy dt over dx dt. We just took 2 derivatives instead of 1. We took 2 derivatives to form the parametric derivative. Same thing here. We're going to take and we're going to form a derivative by looking at the derivative of y and the derivative of x with respect to theta. Okay, now it's going to be a little bit of a jump. It's not quite as simple as it was in parametric because of this. So we know our 4 equations that take us back and forth. The 2 primary ones were x equals r cosine theta, and the second one was our sine theta. We are going to use those 2 equations to take our polar curve and write it parametrically. So what we're going to do is write our polar curve in parametric form. So we're going to use these 2 equations. But we have to remember that in polar, r is a function of theta. Right? If we have r equals sine theta plus 3, that's a polar curve. R is a function of theta. So this r here, so far what we have been seeing is that this r has been represented with a constant. We're changing that now. When we change our polar curve over to parametric, we're going to take our polar curve and plug it in right there for r. We're thinking of that r as a function now, not just a constant. And if we do that, then we differentiate the y with respect to theta, and we differentiate the x with respect to theta, and we get that formula there. There's no point in remembering that formula. This is what you want to remember right there. Just y prime over x prime. You could memorize this if you wanted, if you're one of those folks that likes to memorize crazy looking things, but it's much better just to think of the derivative like we did parametrically, y prime over x prime. That's the simplest way. So when we look at this polar curve here, which we now know is a circle tangent at the origin, right, we just graph those things, and maybe we should graph this real quick just as a reminder. As you practice this, if you get into that habit of doing the pi over 2 rotation thing, it's pretty quick to graph. What's cosine of 0? So cosine of 0 is 1. Multiplied by 2, we get 2. So we're going to be 2 units over here. And we're already done, because all of these circles are tangent at the origin, so you already know what the next point is. The origin's always one of the 2 points. And if the first point's not the origin, the second point is the origin. So if we go up to pi over 2, cosine of pi over 2 is 0. 0 times 2 is 0. We're here. And we already have it in our mind that, oh yeah, constant times sine or cosine is a circle. So we know that this is what that circle is going to look like. So we're dealing with that function. That's a polar function. It's certainly not a Cartesian function because it doesn't pass the vertical line test, but it is a polar function. You plug in 1 theta, you get out 1 r. Yeah, so you can think of that as a polar function. Okay, so let's form our parametric. So the parametric representation, is x equals r, so there's r, multiplied by cosine of theta. Right there. So r cosine theta. So we just take our polar function and replace the r with it. And then our second equation, so these are our polar parametric equations. So there we go. There is the parametric form of this curve here. And if we simplify this a little bit, we have 2 cosine squared of theta. And down here, we have 2. I can't help myself. We always write this double angle thing as 2 sine cosine, not 2 cosine sine. Of course, it doesn't matter. Commutative log multiplication. You could change this to sine of 2 theta if you wanted. We don't need to, but you could. If you wanted to, it's nice just because the derivative would be easier, but let's not do it. Okay, so there is our parametric form. Now to get our derivative, we're going to need the derivative of x, and we're going to need the derivative of y. So let's just create a derivative system here. The derivative of x, we're going to get 4 cosine to the 1, so 4 cosine theta. Pop the 2 down, subtract 1 from the exponent. But then we have to multiply by the derivative of the base. The derivative of the base is negative sine of theta. So we're going to have that and this. Now for the second one, we have to use the product rule. So we're going to think about this as first function and think about that as second function. Now if you wrote it as sine of 2 theta, that would actually be easier to differentiate because then it would just be cosine 2 theta times 2. So you could do that, but let's just suppose that you can't always do that. So let's do this as a product rule. So we have first function. Derivative second function is negative sine of theta. So we're going to have that. Sine of theta times negative sine of theta. So first derivative second plus the derivative of the first is 2 cosine theta multiplied by the second. That gives us another cosine of that. So therefore, now we know our derivative. So dy dx, slope of the tangent line, is going to be negative 2 sine squared of theta plus 2 cosine squared of theta, all divided by negative 4 cosine theta sine theta. Once again, I can't help myself. We always see it in the books as sine cosine. So we have that. And we could simplify this. We could do one simplification step. We could divide out a negative 2. We divide out a negative 2. That would look a lot nicer. Okay, so there is our derivative function. Function of theta. All right, now this question said nothing about where to take the derivative, but let's do it at a few points. And let's think. So we saw that theta equals 0 was over here. What do you think dy dx should be when theta is 0? This tangent line is vertical, so what'd you say?
Non-existent.
Right, so we should get something undefined, right? If the point on the curve at theta equals 0 translates to a vertical tangent line, the derivative should be undefined. Let's check. So we come over here, we're going to use that same notation that we use with parametric. We have to put that vertical line with a theta equals 0, so that's what we would do. All right. Sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we're going to get negative 1 divided by 0, which is undefined. That translates to a vertical tangent, which is what we have at theta equals 0. Now theta equals pi over 2 is putting us here, so at pi over 2 we should also get a vertical tangent. And we don't know what the theta value is right there at the top. What did I do? We don't know what that theta value is right at the top. There's a couple of things that, what would you suspect it might be? What would be ideal? If theta equals 0 is here and theta equals pi over 2 is there, so this one over here is theta equals pi over 2, what would you hope? So theta equals pi over 2 is there. What would you hope would be the theta value that graphs the top?
Pi over 4.
Pi over 4 is what we would hope. We can tell very easily because what should the derivative at pi over 4 be? Not quite. Try again. At the top of this circle, what should the derivative be?
0.
The derivative, we have a horizontal line. So if pi over 4 truly generates the top of the circle, the derivative should be 0 because a horizontal tangent line has a slope of 0. So let's see. So if we plug in pi over 4 into this messy looking equation here, sine of pi over 4, you can write it, sine of pi over 4 as root 2 over 2 or 1 over root 2. Those are the same things. In this case, it's a little easier to think of it as 1 over root 2 because then you're squaring it and you just get 1/2. So we would have 1/2 minus 1/2. Sine and cosine are both 1 over root 2. So all right, the numerator is 0. We're going to get 0 unless the denominator is also 0. Let's see. So denominator is not 0 though. So 1 over root 2 here, 1 over root 2 there. So these two multiply together to 1/2. And then 1/2 times 2 is going to be 1. So this is going to be 0 over 1, which is 0. So that is going to correspond to a horizontal tangent. So sure enough, this point right here is in fact plotted when theta is pi over 4. So 0, pi over 4, pi over 2. What do you think this point? What do you think the theta value is for that point? So we had 0. Say again?
1 pi over 4?
3 pi over 4. So we're going by pi over 4s, right? So 0's here, and then pi over 4 is going to be there, and then we had another pi over 4 is going to be there, and then another pi over 4 is going to be right there. Do you see that the radial value is going to be negative? Right, if we plug in 3 pi over 4, 3 pi over 4 is an angle in this direction in quadrant 2. But if we're going to plot that point down there, we're going to have it's going to be a negative r value. Okay, so, all right, so let's go to there. If you are a glutton for punishment, you could just memorize this formula. Again, I highly recommend not spending time memorizing that formula. I think it's much easier to do what we just did. Convert your polar curve to parametric with r cosine theta, r sine theta, and then do the parametric derivative, y prime over x prime. If you want to, you could just memorize this whole crazy looking formula. That will work. So, one observation I want to make here is that if we have a curve that passes through the origin, so we pass through the origin there, the function value is 0 when the curve is passing through the origin, right? The radial value is 0 when you're passing through the origin. Everyone okay with that? So if the function is your radial value and you're going through the origin, when theta is equal to theta sub 0, theta naught, then f of theta naught is 0. The r value is 0. So if you look at this, if you're at that point right there, then this is equal to 0, and this is equal to 0. So the derivative would reduce to just this. Okay? So if the curve is going through the origin, the radial value is 0 here. So the radial value is the function. So if we have a theta value, namely theta sub 0, and you plug it in there and you get 0, then these two are gone. These two coefficient pieces here are going to cancel. That's going to cancel with that. So what do you end up with? Sine of theta naught over cosine of theta naught, which is tangent of theta naught. So if you have a curve through the origin, the slope of the tangent line is just tangent of whatever the theta is that generated that graph of the origin. Question, Daniel? No. You have that look like, you have a puzzled look. So, do you agree that if we're at the origin, the r value is 0? So if we're plugging in theta equals, say, pi over 3. If we plug in theta equals pi over 3, we're getting 0. That plots the origin. Okay, well, if pi over 3 has an r value of 0, same thing, f value, r value, because the way the book introduces a new letter. You don't have to introduce a new letter, but they always like to. Then the function value is 0 for both these, so those two terms are gone. Both of these terms have an f prime of theta 0, so those just cancel out, and you're left with sine over cosine of the same angle, which is tangent of the angle. So if you have a curve that goes through the origin, the slope of the tangent right there is just tangent of theta 0. You can, of course, go through what we just did, and it will work. You'll get the right answer. This is just more of an observation. If we take our polar curve, convert to parametric, do dy over dx, we'll we'll get the right answer there. But that's more of an observation. Okay, so let's take our break. Take our break, and then we'll do some polar calculus. And then we'll be done. Polar calculus is going to be the end of the new material. Cartesian calculus sometimes just isn't. What am I doing here?
Right now, the circle graph.
There we go. On with some calculus. Favorite subject. Unless you're a computer science major.
You can use your foot, and you're proficient, you can do the entire job.
Okay, so we have a polar curve presented to us. We do not know what that looks like. If it was a constant times cosine theta, we know that that's a circle that's tangent at the origin. But that's a double angle, so it's more complicated. We don't know what that looks like. We can plug it in Desmos, which is a great tool for graphing polar. The only polar curves you need to know how to graph are those circles tangent at the origin and the cardioids. Those are the only ones that I will ask you to graph. If it's some other thing, I will give you the graph.
By asking us to graph, you mean it'll be on the final?
Yes. Yeah, that's very precise. That is right.
That's one of the 3 questions.
So there's 4 questions from each exam and 4 from this new stuff.
Are we allowed to have new material?
Yeah,
on
you
the
can.
card?
I don't care.
Ah, nice.
Yeah, I know. Merry Christmas. Oh, happy summer. So
It'll make it easier for you to grade if you allow that.
I know.
Everyone gets up.
That's true. All right, so these things are called roses.
Not change our.
So there's our cool looking graph. And if you start playing around in polar where you start fiddling with the angle, you get all sorts of crazy stuff. So there is our graph. And of course, what do you think happens if we increase the coefficient of the angle?
More petals.
So if we put a 4 here, how many petals are we going to have?
8.
Yeah.
Oh, so if you put a 3, will it be 3 petals?
Ah, now if we put a 3, if we put an odd number, everything is different. If you put an odd number, what you do is graph the thing twice, and you can't see that there's really 6 petals if you went from 0 to 2 pi. So if you have an odd number, well, that's not an
Oh,
odd
does
number.
that mean that your domain is restricted?
Yeah. So if you do it from 0 to pi, then you'll get exactly 3 petals. But if you did 0 to 2 pi, you get 6. But you can't see the other 3 because they're on top of the other ones. So even is just going to be double whatever that coefficient is. Odd is going to be exactly that coefficient. Okay, so this tells us or asks us, no, it's telling us, find the slope. So find the slope of the tangent line at the following polar point. So here is our polar point. And let's just get a sense of what our answer should be by looking at the graph. So if we go to pi over 2, right there, and plug pi over 2 into this function, pi over 2 goes in for theta. 2 times pi over 2 is pi. So cosine of pi is what we have to evaluate. Cosine of pi is -1. -1 times -4 is +4. So in the pi over 2 direction, we are in fact right there. We're going 4 units in the pi over 2 direction. What should the slope of the tangent be there?
Undefined.
No. That's horizontal.
Oh,
0. Vertical is undefined.
sorry.
Think of it like skiing. If you ski down this slope, you will be undefined. Right? Ski on that slope and you're going 0 miles an hour. So that tangent line is going to be horizontal. Slope will be 0. So we know what we're supposed to get. So let's see if we can get it. All right. So polar to parametric first. So switch our polar curve. We're going to go to parametric because then we can just do dy over dx by doing y prime over x prime. So we take our polar curve, that's the r. So r is now a function, r cosine theta. And then down here, we do r sine theta. So now we have the parametric representation of the rows, or the four-petaled rows. And we can't combine here because this is a double angle, that's a single angle, double angle, single, so there's no simplification here. I'm just going to leave it like that because we kind of have first function, second function. It'll be easier to differentiate. So let's do it up here. So let's take the derivative of each of those with respect to theta. So the top one, first times derivative of second. The derivative of second is negative sine of theta. So this is going to be 4 cosine 2 theta times sine of theta. So that's first derivative second, plus the derivative of first times second. The derivative of first. We come into the function. The derivative of cosine is minus sine of 2 theta times 2. So minus sine is going to make that a positive. But then we have to do our chain rule, so we're going to get an 8, and it's going to be this, sine of 2 theta. Multiplied by that, cosine theta. So everyone okay with that? So derivative of first, negative cosine 2 theta times 2, times negative 4. Now we do the same down here. We do first derivative second. So that part's easy. But then we do the derivative of this, which we already did, and multiply by sine. So this one's going to be 8 sine of 2 theta times sine of theta. So we get that. Now, we want the slope of the tangent at this particular point. If we wanted to, if the question said write down dy dx, which it doesn't say to actually write dy dx, like that's kind of a pain just to rewrite those things for the sake of rewriting them. But you could, we could rewrite dy dx as this over this. If we're going to do it, we should at least simplify it all in the same step instead of rewriting that whole hideous thing twice. So let's try to do it, but let's try to do 2 steps in one. So what are we going to divide out from everything? We're going to do y prime over x prime. Divide out a 4. OK, so y prime, let's just divide out. We could divide out a negative 4, but there's only one negative, so I'd rather divide out the positive. If there's 3 negatives, then I would say divide out the negative. So if we're going to divide out just a 4, we are going to end up with negative cosine 2 theta cosine theta plus, divided out the 4, don't forget, we divided out the 4. Yeah, doing 2 steps in one sometimes it's not the best move. Here it's okay, I think. Divide out the 4 there, cosine 2 theta times sine of theta plus 2 sine 2 theta cosine. All right, so there's your dy dx. That is the slope of the tangent line. Right there. And this said, let's find the slope of the tangent line at pi over 2. So I'm just going to move this a skosh to the left. So if we want to evaluate this dy dx at theta equals pi over 2, we notate it this way. So we're plugging in pi over 2. When we plug in pi over 2 right here, we end up finding cosine of pi. Down here, we end up finding cosine of pi. OK, cosine of pi is a -1, not a 0, so let's just ignore that for a moment. Come over here, plug in pi over 2, and what's cosine of pi over 2? 0. So this term right here, I'm going to highlight the terms that are going to go to 0 instantly. That term and this term are going to go to 0 instantly, correct? Because cosine of pi over 2 of both of those is 0. Okay. Now we come down, let's go to this one. So plugging in the pi over 2 here, this is great because this becomes sine of pi, which is 0. So the whole numerator definitely becomes 0. And now we're just hoping that the whole denominator doesn't become 0 because then we have an indeterminate form. And so like we just plugged in pi over 2 down here a moment ago, cosine of pi is -1. And sine of pi,
Sine of pi over 2.
oh, thank you. Okay, thank you. We're plugging in pi over 2. So cosine of pi is -1, sine of pi over 2 is 1, so we get a -1. So we get 0. Yeah. Plugging in pi over 2. Plugging in pi over 2 makes that angle pi and that angle pi over 2, so we end up with 0, which matches what we have over here. This point is theta equals pi over 2. Good. All right, let's try another one down here. Any questions on that? Everyone see how we did it? Come on, stretch. Put one line. Okay, so once again, we have a curve that we don't recognize. If it was 4 plus 4 sine theta, it would be a cardioid. Right? If it's just a constant times sine, it's a circle, but if you add that shift, then it becomes a cardioid. So 4 sine theta would be a circle, but then if you add 4, then all of a sudden it becomes a cardioid. So we don't know this one because those two constants are different. And we have a coefficient of 1 in front of the sine. So if that was a 4 or a -4, we would know what it was. It'd be a cardioid. So we don't know what it is. So let's just go to Desmos real quick and change this to 4 plus sine of theta. So this is a shifted, it looks like a circle. Now we don't know for sure if it's a circle until we do some more math, but it does look like a circle. But this is not one that you need to know. You do not need to know this one. All right, so let's plop it in there. All right. So certainly looks like a circle. All right, let's do the math though. So this polar curve first gets converted to parametric because it's easier to find a parametric derivative. Y prime over x prime. So x is going to be r, 4 plus sine of theta, r times cosine theta. And then r times sine of theta. Right. So those are the parametric equations for this polar curve. Or that circle thing. Looks like a circle. Probably is. Derivative system. First, derivative second. So first, the derivative of second, derivative of cosine is minus sine of theta. So there's first derivative second. Plus the derivative of first, which is cosine, times second. So we have cosine multiplied by cosine, which is cosine squared. Y prime. First derivative second. So first is going to look like that. Derivative second is cosine. Plus the derivative of first, which we already said is cosine, but this time it's multiplied by sine. Okay, now this one we have some simplification we can do also. If we're going to rewrite this whole thing, let's try to do 2 steps in one. So y prime will be 4 cosine theta and then if we distribute the cosine here, we're going to get sine cosine, and here we get sine cosine, so it's 2 sine cosine. Well, we might have been able to cancel the 2. Let's see. So up here, we're going to have minus 4 sine of theta. So minus 4 sine of theta, and then minus sine squared plus cosine squared. Well, I guess we couldn't do. Good. All right, so we have that. And some of you probably are noting that, ooh, aren't those double angles? And yes, and you could convert to double if you wanted to, but it's not going to help us that much. Right? Both of these are double angles. This is sine of 2 theta, and this is cosine of 2 theta. So you could do that, but we don't need to. So there is our derivative. So this tells us the slope of the tangent line at every point on our graph. They ask us to find the slope of the tangent line at 3 pi over 2. Let's see if we can sort of forecast what we might get. So if we're plugging in points, 3 pi over 2 is all the way down there. If we plug in 3 pi over 2 there, sine of 3 pi over 2 is negative 1. 4 minus 1 is 3. So okay, this is in fact where we are when theta is equal to 3 pi over 2. So that tells us that we should get 0. So we should get 0. That has a horizontal tangent. Let's see if we do. So plugging in 3 pi over 2 into the numerator. Cosine of 3 pi over 2 is 0. 3 pi over 2 at cosine value down here, cosine value is 0. So the numerator is definitely 0. The denominator, 3 pi over 2. Let's highlight all the things that go to 0 with yellow. So that's going to go to 0. That's going to go to 0. Cosine of 3 pi over 2 is 0, so that's going to go to 0. Let's then focus on what's left in the denominator. So sine of 3 pi over 2.
Negative 1.
So negative 1 times negative 4 is 4. And then here, again, sine is negative 1. We square it, we get positive 1, but we have a minus there. So we're going to end up with 0 divided by 3, which is 0. So we're getting what we expected to get. Getting what we expected to get. All right. Any questions on tangent lines? All right. Horizontal and vertical tangents. Negative 2 sine theta. Circle or cardioid?
Circle.
Yes. Negative 3 minus 3 sine theta. Circle or cardioid? Cardioid. Good. All right, so this one. Let's do this circle first. And you can try to memorize whether it's shifted up or down or right or left if you want, but it's very quick because we've seen you only need 2 points. Plug in theta equals 0. Sine of 0 is 0, so your first point is in fact right there. Second point, we plug in pi over 2. Sine of pi over 2 is 1. 1 times negative 2 is negative 2. So in the pi over 2 direction, we go negative 2, so we go down. So we're going to be down here. And we know it's a circle. That's going to be enough in this case. So there's our circle. How many vertical tangents should we have? 2. How many horizontal tangents should we have? 2. All right, so we're expecting to find those 2 horizontal tangents, and we're expecting that we're going to have these 2 vertical tangents. So we need to find dy dx. To find dy dx for a polar curve, we convert to parametric and then do y prime over x prime. So let's go. So our parametric representation, x equals r multiplied by cosine of theta, and y equals r multiplied by sine of theta. These can both be kind of rewritten pretty easily. So minus 2 sine theta cosine theta. And down here, minus 2 sine squared. Okay. Now we have to take our derivatives. So we've got our functions. This time, let's do it a little differently. This time, let's use a double angle for this one. 2 sine cosine is sine of 2 theta. You don't have to, but let's do it this time. We didn't do it last time. So now we've got this one we're just going to leave as is. So there's our x, there's our y. Let's find our derivatives. So the derivative of x, cosine 2 theta times 2 with a minus sign in front. So cosine 2 theta times 2. This one we have to use the chain rule. So it's going to be negative 4 sine of theta to the 1. Pop the 2 down, subtract 1. But then we have to differentiate the base. We get cosine of theta. There's another double angle if we want to change it. Right, this one we could write as negative 2. And then we have a 2 sine theta cosine theta, so that becomes sine of 2 theta. So this time let's do it. Let's go with double angles. Just for grins. So dy dx is going to be the y prime over x prime. The negative 2's cancel. Y prime over x prime. So we're going to get sine 2 theta over cosine 2 theta, which we could write as tangent of 2 theta. That makes things messy, though, because in order to find vertical tangents, we're trying to figure out where the denominator is undefined. And to find horizontal tangents, we're looking for where the numerator is undefined, or where the numerator is 0. So let's just leave it like this. So we're going to take the numerator. Let's figure out when it's equal to 0. All right, so we're back in trig now. We're solving a trigonometric equation with a multiple angle. So here is the best way to do it. Draw a picture. And we want to know the angles where sine of 2 theta is equal to 0. So in order for this to be true, 2 theta has to be either there or there, right? So the place at which sine is equal to 0 is either on the left side of the unit circle or the right side of the unit circle. Right? The second coordinate has to be 0. So this tells us then that 2 theta is equal to, if we wanted to be super type A, we would say 0 plus pi times k. And that would give us a million solutions. More than a million solutions. But we know that we've already talked about the fact that this circle is graphed between 0 and pi. There's no need for us to go beyond pi. We've seen that this whole circle gets graphed when we go from theta equals 0 to pi. So it's enough for us to just look at these 2 possible solutions. And if we divide by 2, theta will equal 0 or pi divided by 2. Say again?
Couldn't you also put pi?
You could also put pi. Let's think back. When we're parametrizing and we're going around, do we want to include the very last value of theta? We don't want to include that very last theta value because then we'll have, well, a circle plus an extra point. So if we graph it from closed at 0 to open at pi, we'll get exactly one pass of the circle and not an extra point. All right, so those are the values of theta that are going to correspond to what? When the numerator is 0, are we getting horizontal or vertical tangents?
Horizontal.
So a horizontal tangent is when the value of the derivative is 0. So if the numerator is 0, these are potential horizontal tangents. Now there is a problem if both top and bottom are simultaneously 0. But if we want a horizontal tangent, we need the numerator to be 0. So these are our potential horizontal tangents. And of course, we see there's 2 of them, and we have 2 values here, so it's going to work out fine. Let's just double check. When you plug in 0 down here, do we get a 0? Cosine of 0 is not 0. If you plug in a pi over 2, cosine of pi is not 0. So these are zeros of the numerator and not simultaneous zeros of the denominator. All right, let's go denominator now. Actually, let's move this thing. Can I just grab that thing and move it? So let's go with the denominator now. So now we're looking at potential vertical tangents, where the denominator is 0 and the numerator is not simultaneously 0. So again, let's go unit circle. So the best way to deal with these multiple angle equations is to look at a unit circle. We want to now identify this function is going to be, if we set it to 0, cosine is 0 at these 2 positions. So that tells us that the angle, so if we set cosine of 2 theta equal to 0, that tells us that the angle, which is 2 theta, has to be either pi over 2 or 3 pi over 2. Now again, if we were super type A, we'd say, oh, it's pi over 2 plus pi k, where k is an integer. That would give us all the bazillion solutions. But we know we just need the first 2 positive ones. Those because we see that we've got 2 vertical tangents. So this tells us that theta is equal to, if we divide both sides by 2, we get pi over 4 or 3 pi over 4. So these are going to be vertical tangents. As long as the numerator is not simultaneously 0, of course it's not. If we plug in pi over 4 there, sine of pi over 2 is not 0. If we plug in 3 pi over 4 there, we get sine of 3 pi over 2, which is not 0. So these are the angles where we have vertical tangents right here. And these are where we have horizontal tangents right there. So this says find the points at which the following happens. So these are the angles where it happens. So the book's not super clear on whether we want to write our points in polar or write our points in Cartesian. So you could do, if it's vague, you could do either. You could do either. So if we are given angles, it probably is a little easier to do them in polar. You could convert to Cartesian, but that's going to be more work. Let's not go with more work. All right, so the points then are, we do r comma theta. So our 2 points, theta comes second, even though we sort of think about plugging in theta values. Let's see. How do we find these? So these are polar. I'll just put a little p just to emphasize. How are we going to find the r values for each of those? Yeah. How are we going to get the r value?
Is it the radius just of that little circle?
So r here is a radial value, but not necessarily the radius of the circle. But we do just plug into this equation, right? So this tells us how far away we are from the origin at different theta values. So if we have theta equals 0, we plug that in, sine of 0 is 0. So that's going to be the origin. Like if you were just to look at 0, 0, it's hard to know if it's in polar or Cartesian. It's actually the same point, so it doesn't really matter. But If we plug in pi over 2, sine of pi over 2, 1. 1 times negative 2 is negative 2. So the r value here is negative 2. And let's just visualize this. So when we go to pi over 2, that's pointing up, but the r value is negative. So yeah, we're down there, down at the bottom. So those are our 2 points where we have horizontal tangents. So these are horizontal tangents right there. And then if we want the vertical tangents, these guys, we know that the angle is pi over 4. That comes second. It's r comma theta. So we have this and this. And if we want to get the r value, same thing. We're just going to plug in those thetas here. Plug in pi over 4. Sine of pi over 4 is root 2 over 2. So this is going to be minus root 2. And then we plug in 3 pi over 4. Sine of 3 pi over 4 is also root 2 over 2. So root 2 over 2 times that is going to be negative root 2. And this will be our pair of points where we have vertical tangents. Let's check. So the top one, pi over 4 is in quadrant 1. And we're supposed to go negative root 2 in the radial direction. So because it's negative, we're going to come down, and this point where it's going to hit right there is that top one. So pi over 4, negative root 2 over negative root 2. So that distance right there is root 2, which makes perfect sense because this is negative 1. Negative 1, so the diagonal of that square that's a 1 by 1, the diagonal of a 1 by 1 square is root 2. And then similarly, if we go to 3 pi over 4, which is in quadrant 2, then we have to go backwards root 2, which is going to put us right there. Okay? Now let's do a cardioid. First, let's graph this cardioid, just so that we have a visual cue for what the graph just helps us know what we're supposed to get. So do our 4-point check here. Plug in 0, sine of 0 is 0, so negative 3 is backwards 3, so right there. Everyone agree with that? Make sure that that makes perfect sense. If you plug in 0, you get negative 3. So in the 0 direction, you go in the opposite direction 3 units. Pi over 2. Sine of pi over 2 is 1. Negative 3 minus 3 is negative 6. So in the pi over 2 direction, we go negative 6, which is down there. So that's pi over 2. So this was theta equals 0. Theta equals pi over 2. Theta equals pi. Sine of pi is 0. We're at negative 3, so pi is just zipping us back over here. And we know where the last point has to be, because for a cardioid, it's always a triple, collinear triple. We know it's going to be the origin, but we'll plug it in just to make sure. Plug in 3 pi over 2. Sine of 3 pi over 2 is negative 1. Neg 1 times neg 3 is positive 3, so we get 0. So that's 3 pi over 2. Okay, now if you look carefully at a cardioid, it's not totally, it's not totally obvious, but there are clearly 3 horizontal tangents here. There's going to be one right there. There's going to be one right there. There's going to be one right there. The question it has to do in this case with the vertical tangents. There are obviously the 2 on the edges. Say again?
Like a little crevice.
Yeah, and that little thing in there will be a vertical tangent there. So for a cardioid, regardless of what direction it is rotated, there will always be 3 horizontals and 3 verticals. Okay, so that is in fact coming in steep enough that it forms a vertical tangent at the dimple. We will have a vertical tangent. So let's go ahead and deal with this. So first we go to parametric, because a parametric derivative is a lot easier than that polar derivative with that hideous formula. So x is equal to r multiplied by cosine of theta. Y is equal to r multiplied by sine of theta. Does not seem advantageous to distribute the cosine or the sine. We have to use the product rule no matter what. So let's just use the product rule with the way I've got it isolated. So derivatives. So first derivative, second. So first, and when I take the derivative of second, I get negative sine of theta. I'm just going to push that negative sign inside there to offset those negatives. Derivative of cosine is negative sine, so we'll distribute the negative to make everything positive on the inside. So first derivative, second, plus the derivative of first. Derivative of first is minus 3 cosine of theta. I guess I don't need this parenthesis here. So negative 3 cosine of theta multiplied by cosine of theta. So derivative first, minus 3 cosine theta times cosine. Second one, we have first derivative second. Derivative second is cosine. Plus derivative of first times second. Derivative of first again, we just did it up there, negative 3 cosine theta. But then we multiply by sine. Well, there's our product rule. There is some simplification here. Let's rewrite this. Let's simplify it a little bit. It'll help us in the long run. For this one up here, we have 3 sine of theta, and then 3 sine squared of theta, minus 3 cosine squared of theta. And down below, I think we get some cancellation, or at least some combining. We're going to get minus 3 cosine theta, and then minus 3 sine theta cosine theta, but then minus 3 sine theta cosine theta again, so this is going to be minus 6. We're almost to our derivative. So dy dx will equal, what do you want to cancel out?
3 or negative 3.
Which one?
Negative 3.
All right, let's cancel out a negative 3. It does not matter which. So if we divide everything by negative 3, we're going to get negative sine of theta, negative sine squared of theta, and then plus cosine squared of theta. Divide out a negative 3 here, we get cosine of theta. Divide out a negative 3 here, we get plus 2 sine theta cosine theta.
I think that's upside down, the dy and the dx.
Oh, did I do it upside down? Oh, shoot. Yeah, I did. Thank you. It's probably not an easy way to flip. Let's cut. Huh.
Just paste it off to the side and then move it.
Yeah, but usually it doesn't disappear, though, and I can't make a right click on the board.
Yeah.
Usually I thought it just stuck around.
Someday
Interesting.
with Neuralink, the professor can just think of a graph and it'll just show up on the screen.
It's not going to be long.
No.
It's not going to be long.
Will be the professor, will be all the students, will be our
Yeah, you can ask a question with Neuralink, it just shows up there. Crazy.
But you wouldn't even need to ask the question because your girl would just answer it for you.
Oh, the world is weird.
You have to put a magnet on your skull when you take the test so you can't cheat.
You had a friend that used to teach physics at Horizon High School for 1,000,000 years. and he was so pissed off at all these students with these cell phones that what he did was ordered from China a frequency blocker, which is completely illegal to do this in a school, but he would stick it in the storeroom in his physics classrooms. No one's phones would work. And he never got busted by the administration. It's so funny. Okay. All right, so there is our dy dx right there. There's the slope of the tangent. All right. So now we need to set the top and the bottom each equal to 0. The top is finding when the top is 0, we're finding horizontal tangents. When the bottom is 0, we're finding vertical tangents. So let's go with the numerator first. So numerator are potential vertical tangents. And I say potential because you could have a indeterminate form. So we're going to set the top equal to 0. In setting the top equal to 0, we are going to factor cosine to the front so that we have a product of functions equal to 0. So we can use the 0 product rule.
Would top to 0 be horizontal or vertical?
I said horizontal, but then I wrote vertical. Yeah, top 0 is horizontal. Because if the derivative is 0, we're going to get horizontal. Thank you. So this tells us that cos theta is 0 or sine of theta is -1/2. So we look at our unit circle. Let's figure out where we are in the unit circle for those particular values. Cosine is 0 here and here. Sine is equal to -1/2 there and there. We look at our graph, there's 3 horizontal tangents, but we have 4 zeros. So we'll have to be crafty here. So theta is equal to, let's just go in order, pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. So there are the 4 zeros. Those are our potential horizontal tangents. Now let's go for our potential vertical tangents where we have an undefined derivative. So that's where the denominator is 0. It's going to be a little bit trickier. We need to create a 0 product setup so that we can set them each equal to 0. Does anyone see what we need to do in order to make that an option? Anyone see what we need to do to make that an option? Because when we look at that, that is not factorable as it is presented to us. Is there something we could do to make it factorable?
Convert cosine squared to...
So if we convert these cosines here to sines, then we'll have one trig function that we could then factor like a trinomial. So cosine squared is 1 minus sine squared. So that is exactly where we're at. So this is going to be, let's think about moving everything to the other side so the sine squareds are positive. So sine squared, we want a leading coefficient that's positive. It's just easier. So 2 sine squared plus sine minus 1 equals 0. Two sine squared. It's like, wait, that's not factorable. Yeah, now it is. Now it's factorable. So this is 2 sine theta. This is sine theta. And we have to have a 1 and a 1. And should the negative be in the first factor or the second factor?
The second.
So if it's in the second factor, the outer is going to give us -2 sine theta, and the inner is going to give us +1 sine theta. So when we combine those, we'll get -1 sine theta. So we want the negative to be able to hit the 2 to make the bigger combination negative. All right, so this tells us then that sine of theta is negative 1/2. That sounds familiar. Sine of theta is negative 1/2, or sine of theta is 1. All right, so that's going to give us, let's draw our circle right above it. So this is going to give us the following places. We'll go purple this time. So there, and sine of theta is 1 right there. Something seems fishy. Because we have 2 that are overlapping. There's a sign wrong somewhere.
Should it be negative? Should it be plus sine theta in that middle one?
So that is the error right there. So sine squared goes to the right, sine squared goes to the right, giving us 2 sine squared. Minus sine goes to the right, making this positive, which then switches these two. Yes. So then this is positive sine, positive 1/2 here, and negative 1 right there. Yeah, there can't be that many that are overlapping. So then our circle, let's get those guys matched up. So we have 1 that's overlapping right there. And then sine is equal to 1/2 here or here. So our angles are theta equals pi over 6, 5 pi over 6, 5 pi over 6, or 3 pi over 2. Okay, so now we see this conflict. Right there. We know from looking at the graph that there's going to be 3 of each. This only has 3 zeros. That is going to correspond to our 3 green vertical tangents, no matter what, because there's got to be 3 verticals and there's got to be 3 horizontals. The other ones, so these ones are all going to be vertical tangents, no matter what. These ones, this one is extraneous up here. That one is not going to create a horizontal tangent. The other 3 will create horizontal tangents, but that one is not going to. Now, if you wanted to do the math, I'm not going to ask you to do the math. We're just going to use common sense and logic and say, oh, there's 3 of each. And if there's 3 of those, then this one must be extraneous up there. The book does go through the process of showing you how to know which one it is. What this is showing us is that at 3 pi over 2, we have an indeterminate form. And so what we have to do, if we were to evaluate it, when we plug in 3 pi over 3 pi over 2, we're getting 0 over 0. So what we would have to do is take a limit as theta approaches 3 pi over 2. So we would take the limit of this as theta approaches 3 pi over 2. And if you take the limit of that as theta approaches 3 pi over 2, you are going to end up getting a vertical tangent. You're going to end up getting the derivative to be undefined. So that's how you would do it if you were asked to do it. We're not going to do it. They do it in the book. If you look in the online textbook, they have an example where they walk through. Okay, we have an indeterminate form. We have to take the limit because we have an indeterminate form. And they'll work it out. As far as we're concerned, though, we can use common sense. And we know that there's 3 of each. So if we've got the 3 horizontals, then the one that's duplicated is going to be indeterminate for whatever group has 4 instead of 3. Okay, so vertical tangents, horizontal tangents. Well, let's go to area, our last topic. The final topic. Area, polar area. Don't skip it. It's not crazy hard. But of course, it's another ball in the air. Okay, so our last topic, polar area. You all have worked with sectors before, and you should know the area of a sector. Can someone remember the area of a sector of a circle? So if we have this sector here, there's the R, this is the S, that's also R, which we don't need to write twice. This is theta.
Did we say it was theta?
It's so if it's a unit circle, theta and S are equal. So if we want the area, you may not remember, it's 1/2 theta R squared is the area. In order to get that, you just take the ratio of the full circle area, pi r squared, and then you take a ratio of it, and that ratio is going to be theta over 2 pi. You're taking theta, you're taking a portion of the full circle. But whatever it is, however you want to get to it, this is the area of a sector of a circle, 1/2 theta r squared. That is the area of a sector. All right. When we visualize a polar curve, we are imagining these radial lines that tell us how far to go out from the origin. When we go the Riemann sum approach, the geometric shape that's going to be used to approximate the area, which we don't call area under the curve like in Cartesian. This is just polar area. Polar area is going to mean basically to the origin. Each one of these, instead of rectangles, we have each one of those little sectors. So the polar geometric approximation is with sectors, slices of pizza, instead of rectangles. And so the idea is the Riemann sum idea. You partition it, and then you have more and more sectors, and the more and more sectors you have, the closer your approximation is. You take the limit, and when you take the limit, you get exactly the area. So the area, 1/2 theta r squared, the variable that's the incremental variable in Cartesian is normally x. Right? You do a delta x. They're getting tinier and tinier. Here, our incremental variable is theta. Right? As theta gets tinier and tinier, our sector gets tinier and tinier. So theta is going to be the incremental variable. That's going to turn into a d theta when we take the limit. And so the approximate area is this, 1/2 theta r squared. You don't need to know the Riemann sum. Not important. What's important is that when you take the limit of a Riemann sum, you get area. So the Riemann sum is an infinite approximation. You have an infinite series, essentially. And when you take its limit, you get exactly the area. So this is where let's look at this formula first. This is the simplest case. So 1/2 theta is the d theta r squared. Alpha, we've already talked about that earlier today. Theta equals a constant is a line through the origin. So theta equals this constant gives us this diagonal line. Theta equals beta gives us that diagonal line. So if we integrate this function, which is r, coming out from the origin, if we plug it in right there, that we're going to find that polar area. So 1/2 r squared d theta is our integral formula. Now, if we have the crazy situation where there's two curves, like we've done a lot in Cartesian, and you want the area between them, in Desmos, I could not shade in between two polar curves. So I could shade that in Desmos, but I couldn't shade that. Could not figure it out. So if we have two curves, then we have a washer analog. All right? We have the outer curve squared minus the inner curve squared divided by 2. So it looks just like a washer. Outer squared minus inner squared. So that is a formula we need to know now, which, remember, on the final, you can have a note card, both sides of a note card, 3x5 note card. So, and you can put formulas from this unit on it. It's totally fine. There's a lot of stuff in this class, so trying to restrict it seems silly. So let's try it. So let's find the area of those alien eyes, or at least one of them. So we've got our alien eyes right here. We want to just find the area of that one. When we're dealing with polar curves, there's some funny business. You know, you get these r's that can be negative and things like that. And it's generally best to maximize symmetry. Sometimes, if this graph, let's just say this graph is graphed, the whole thing is graphed from 0 to 2 pi. Sometimes you can just integrate blindly from 0 to 2 pi and you'll get the whole area. But other times things will start canceling each other out because you have those negative r values. Things can get weird. So the best rule of thumb is to use maximum symmetry. And so when we look at this point right here is when theta is 0. If we plug in theta equals 0 right there, cosine of 0 is 1. So here's where we are when theta is 0. And so as this theta angle is rotating around, if we could figure out how to stop right there, that would be best. That would be the best, simplest way. If we wanted both eyes areas, we'd multiply by 4. If we want just one eye, we'll multiply by 2. Does that make sense? So we want to use the most symmetry we possibly can. So the question then is, as theta is rotating, where does theta get to when we get to the origin? And if you look at the graph paper I have there, it looks like pi over 4. It looks like halfway between the quadrant, the bisecting of the quadrant. It looks like that's going to dump us at the origin. Let's check. If we plug in pi over 4 there, pi over 4 times 2 is pi over 2. Cosine of pi over 2, 0. Cosine of pi over 2 is 0. So that is, in fact, true. And we could look at Desmos to really nail it down. But this should be sufficient. So as theta is increasing, as soon as we hit pi over 4, bang, we're at the origin. So if we integrate from 0 to pi over 4, 1/2 r squared, we will get the area of that red crescent thing. This thing right there. We'll get the red area. So if we want the area of the full eye, we're going to go 2 multiplied by 1/2 r squared. So this is r. We're going to square it. D theta. And we're going to go from 0 over to pi divided by 4. So this will give us the area of one lobe, one eyeball, the right side. That'll do it. The 2.5 cancel. So that's nice. And on the inside, the square and the square root cancel. That's nice. So it all boils down to that fairly simple integral. We'll find the area of the right side. Integral of cosine is sine of the same angle. Then we do our RCR, divide by 2, and then we have our limits of integration. So sine 2 theta over 2. If you plug in 0, you get 0. Yeah?
If we have to find area on the test, will you give us a graph so we know where this is?
Yeah, if the function is something you can't immediately graph, like a circle or a cardioid, definitely. I will give you the graph. So plugging in 0 gives nothing. Plugging in pi over 4, when we plug theta equals pi over 4, we have to double it. So pi over 4 times 2 is pi over 2. Sine of pi over 2 is 1. So the area of one eyeball, one alien eyeball, the area is 1/2. So alien eyeballs, they come in unit. 2 eyeballs, 1 unit. So that shape, obviously it's the infinity shape. They call it the lemniscate or lemniscate, depending on where you are. Figure 8. That's the area. No pi. No pi. All right. Cardioid. Let's graph this cardioid. What is the first point? When theta is 0, how far are we from the origin? 4. The sine of 0 is 0, so we go 4 away. Plug in pi over 2. Sine of pi over 2 is 1. We're 8 away. Plug in pi, sine of pi is 0, we're 4 away. 3 pi over 2, we get 0. All right, so there's our cardioid. It says find the area inside the cardioid. Again, sometimes you can just integrate blindly 0 to 2 pi, but we all know that going through cusps is generally not okay. Turns out in polar, sometimes it's okay and sometimes it isn't. So it's just easiest to avoid the cusp. So if we can do just 1/2 of it, we could do that half, or we could do the other half, does not matter. Maybe the green half is easier because all the thetas are positive, pi over 2 to 3 pi over 2. But you could do the red and go from negative pi over 2 to pi over 2. Does not matter. Let's go green. So if we go green, we are going to integrate from pi over 2 to 3 pi over 2. So pi over 2 to 3 pi over 2. And we saw pi over 2 did put us up here at the top, and 3 pi over 2 did put us down here. So we're using the right angles. And then it's just 1/2, and yeah, we want the full area. So 1/2 r squared. So we take our polar curve, square it, and we're going to integrate that.
Is the whole thing like 2 times that, or is it just that?
So okay, sorry, thank you. We want the whole area. This is going to be just the left half, just the green half. So yeah, so we want the full area, which is what they ask for. Yeah, we have to double it. Yeah, thank you. So the 2.5 cancel. And then we have some shenanigans in here. We need to FOIL this out. There's a couple of things we could do. We could, and I think it's advantageous if we pull out a 16. So those cancel. Oh my gosh. Those cancel. So if we take this 4 and we factor it out, it has to get squared, which will be a 16. And then in here, we'll just have 1 plus sine of theta. That's easier to square. So if we factor out the 4, the 2 in the exponent position is going to square it and make a 16. It's going to leave 1 plus sine squared, which is 1 plus 2 sine theta plus sine squared theta. If you didn't do that, you would just have a 16 there, a 32 there, and a 16 there. How do we integrate sine squared? Back to the unit in the beginning of the semester. We take and we, what do we do?
Turn it like a double angle or something?
Close, yeah. What do we call that?
Oh, power.
Power reduction. Right, we power reduce it, but we have to bump the angle. Power reduce. So 16 out in front, we have 1 plus 2 sine theta plus, and this is 1. There's a cosine of 2 theta. We divide by 2, and the question is it plus or minus for a sine reduction? Sine is negative. So that is what we have to integrate. We'll stop here. I'll just write out the integral. It's, you know how to integrate this by now. I'll write it out though. And that will give us the area of the full cardioid because we doubled it. All right, let's stop there. We have one more slide, which is just a couple of quick problems, which we'll do on Tuesday. So spend your weekend getting up to speed. The final we'll review on Tuesday, but the final is going to have 4 questions from exam 1, 4 from exam 2, 4 from exam 3, and 4 from the new stuff. And if you look in OneNote, there's some good tips. If you look in OneNote, there's some tips on topics down here. If you review, this gives you a good sampling of what the 16 questions on the exam are going to look like. So as you're going through the new material, focus in particular on those 4 topics. It would be super helpful. And have a good weekend. Enjoy the snow.
So you're not gonna make us take the derivative variables of summations and.
The hard question?
Yeah.
That question, do you guys want that question?
No. Quick question.
So the number.
Way rather do binomial.
Yeah. I mean, that hard question will not be on the final.
Cool.
Yeah, that one's caused too much suffering.
That one.
There's been enough suffering.
Yeah, that was.
Enough suffering. Yeah, that one's hard. That one's hard. All right, have a great weekend.
Thank you, you too.
See you during finals week. Thanks, man. Yahoo! I can't believe we're here. Somehow we got here.